So let's take a look at double integrals over general regions. Now, how could we find the double integral of some multivariable function f of x, y described by a general region D? Now, there are two types of general regions. So the first one is type 1. And so if I were to draw a quick graph here, say we have the xy plane here. So type 1 is going to be represented by a region D that is surrounded by two functions. So let's just call this function y equals g2 of x. So y equals some function g in terms of x. And this one, let's just call it y equals g1 of x. So y equals some function g in terms of x. And the x values range from a to b. So as I mentioned, the x values range from a to b, and notice the y values range from the function g1 to the function g2. So that is going to be the range of y values, while a to b is going to be the range of x values. So if I were to write the y bounds in an inequality, I would say from the bottom function, which is g1 of x, to the top function g2 of x. So if I were to rewrite this in an iterated integral, I can rewrite it as the double integral. The outer one is going to be from a to b, the x bounds, and the inner one is going to be the y bounds, so g1 of x to g2 of x, of some multivariable function. Since y bounds are on the inside integral, then I'll write dy first and then dx, because the x bounds are on the outer integral. And so notice that whichever bounds have the variable, or have the variables in them, that is going to be always on the inside integral, because then we can evaluate the double integral. And the ones that have constants like a and b, which in this case are the x bounds, that is going to be always on the outside. So now moving on to type 2 region, the region D is surrounded by two functions here. And so the one on the left is going to be x equals, so I'll rewrite it as x equals some function h in terms of y, so h1 of y, and then the right one, x also equals some function, this time h2 in terms of y. And the y bounds this time range from c to d. So once again, the y bounds range from c to d, so I'll write that there. But this time, not the y, but the x bounds range from the left function to the right function. So I can say the x bounds range from h1 of x to h2 of x. So if I were to rewrite this as an iterated integral, I can rewrite it as a double integral. Since the y bounds are constants, c and d, I'm going to put that on the outside integral. And since the x bounds are variables, that is going to go on the inner integral. So for the double integral, the outer one from c to d, and the inner one from h1 of x to h2 of x. Once again, of some multivariable function f of x, y. Since the x bounds are on the inner integral, I'll write dx first, and then on the outer integral for dy. So once again, the bounds that have the variables are always going to be on the inner integral, and the bounds that have the constants on the outer integral. So the first couple problems, the iterated integral will already be set up for us, so all we have to do is solve. But for the last couple problems in this video, then we'll actually have to find out what those bounds are. So let's say for number 1, we have to evaluate the iterated integral. So the double integral from 0 to 1 and from 0 to x squared of x plus 2y times dy dx. So immediately realize that the bounds that have the variables are going to be on the inside integral, as mentioned before. So we're basically just going to solve this how we would normally solve a iterated integral. So let's go ahead and write the inside integral first. So from 0 to x squared of x plus 2y dy. And so we're going to iterate with respect to y. So x is going to be a constant, y is going to be the variable. So the integral of x is just going to be x times y, since x is a constant, plus the integral of 2y, which is y squared. So now let's go ahead and evaluate from 0 to x squared. And remember, we're plugging these in for the y variable because we integrated with respect to y. So if I plug in x squared for y, we'll get x times x squared plus x squared squared. Minus, when I plug in 0 for y, we'll get 0 plus 0 squared, which is 0. So that will cancel. And so we get x times x squared, which is x cubed, plus x squared squared, which is x to the fourth. So now I can put it under the integral, now from 0 to 1, of x cubed plus x to the fourth times dx. So now we're going to integrate with respect to x. So the integral of x to the third is going to be x to the fourth over 4, plus the integral of x to the fourth, which is x to the fifth over 5. And then we're going to evaluate from the x bounds of 0 to 1. So I go ahead and plug in 1, we'll get 1 to the fourth over 4, so just 1/4, plus 1 to the fifth over 5, which is 1/5, and then minus, when I plug in 0, I'll just get 0 over 4 plus 0 over 5. So that will cancel, and so we're left with 1/4 plus 1/5. Now if I find common denominators here, I can turn 1/4 into 5 over 20, and I can turn 1/5 into 4 over 20. So then when we add them, we get 9 over 20 as our final answer. So now for number 2, we have the double integral from 0 to pi over 2 and from 0 to cosine theta of e to the sine theta times dr times d theta. So realize instead of x and y variables, we have r and theta, but still we're going to treat it the exact same way. And so if I go ahead and rewrite the inside integral, we have the integral from 0 to cosine theta of e raised to the power of sine of theta times dr. And so this might look a little bit tricky at first, but realize that we are integrating with respect to r, not theta. So the entire thing e to the sine theta is basically a constant. So the integral is just going to be e to the sine theta times r. So if we go ahead and evaluate it from 0 to cosine theta, remember those are the r bounds, so we plug them in for r, we get e to the sine theta times cosine theta minus e to the sine theta times 0, which is just 0. That will cancel, and so we're left with e to the sine theta times cosine theta. So now we can integrate it from the outer integral from 0 to pi over 2 times d theta. So now we're going to integrate with respect to theta, and this one's just a simple u substitution problem. So if I set u equal to sine of theta, du, or the derivative of sine of theta, is going to be cosine of theta d theta. So then d theta is going to be equal to du over cosine theta. Now if I go ahead and rewrite the integral, we get the integral from 0 to pi over 2 of e to the sine theta. Now I made u equal to sine theta, so we get e to the u times cosine theta times d theta, which is equal to du over cosine theta. Notice the cosine thetas will cancel, and so we'll get the integral from 0 to pi over 2 of e to the u du, which is obviously just e to the u. So now we can go ahead and evaluate. Well, first I'll substitute back in the u, so back in sine theta here, e to the sine theta, and then we can evaluate from theta bounds of 0 to pi over 2. So when I plug in pi over 2, we get e raised to the power of sine of pi over 2, minus when I plug in 0, e to the sine of 0. Sine of 0 is 0, and e to the 0 is 1, but sine of pi over 2 is 1, so e to the first is e, minus, once again, e to the 0, so then we get e minus 1 as a final answer. So now for these next set of problems, we have to evaluate the double integral. So for number 1, we have the double integral of x cubed y squared dA that is given, or that is described by the region D, and D is inset notation for all xy ordered pairs such that the x values range from 0 to 2 and the y values range from negative x to x. So realize that we just have to turn this into an iterated integral so we can evaluate. So if I rewrite the integral of x cubed times y squared, now realize the y bounds have variables, so whichever bound has variables in them, that is going to be on the inside integral always. So we're going to go from negative x to x. Since these are y bounds, we're going to put dy here, and then the x bounds are from 0 to 2, so that's going to be on the outside because it's a constant. And then I'll go ahead and put dx since the x bounds are on the outside. So now we can go ahead and solve this. So if I rewrite it, the inside integral from negative x to x of x cubed y squared dy, we're going to integrate with respect to y. So this time y is the variable, x is the constant. So the integral is going to be x cubed times the integral of y squared is y cubed over 3. So we can go ahead and evaluate that from negative x to x. Now remember, these are going to be y bounds, so we're going to plug them into the y variable. So if I plug in x into for y, we'll get x cubed times, plugging in x for y once again, so we get x cubed once again over 3, minus when I plug in negative x for y, then we'll get x cubed times negative x cubed is going to be still negative x cubed over 3. And so when I evaluate, we'll get x to the 6th over 3 minus, now this is going to be negative x to the 6th, so minus a negative would be plus x to the 6th over 3. So then I'll get 2x to the 6th over 3. So now that I have found the inside integral, let's go ahead and put this inside the outer integral. So once again, from 0 to 2 of 2x to the 6th over 3 times dx. So now we're going to integrate with respect to x. 2/3 is a constant. I can bring that outside of the integral. So we get 2/3 times the integral from 0 to 2 of x to the 6th dx. And so the integral of x to the 6th is x to the 7th over 7. Don't forget we have that 2/3 on the outside. So we basically get 2 over 7 times 3 is 21, x to the 7th. Let's go ahead and evaluate that from 0 to 2. So then when I do that, we'll get 2 over 21 times, when I plug in 2 for x, 2 to the 7th, minus, when I plug in 0, 0 to the 7th is just 0. Now 2 to the 7th is 128, and 128 times 2 is 256. So we get 256 over 21 as the final answer. So now for number 2, we have the double integral of 2y over x squared plus 1 times dA, described by region D, which is in set notation for all x-y ordered pairs such that the x values range from 0 to 1, and the y values range from 0 to the square root of x. So once again, all we're going to do is turn this into an iterated integral and evaluate. So if I rewrite the integral, or the double integral, of 2y over x squared plus 1, the y bounds have the variable, so that is going to go on the inside integral, and the x bounds have the constants from 0 to 1, so that's going to be on the outer integral. Since y bounds are on the inside, I'm going to put dy first, and then dx on the outside. So now, on to solving it, when I have the integral from 0 to the square root of x, just rewriting the inside integral right now, from 2y over x squared plus 1 times dy. We are integrating with respect to y, so if y is the variable, then this entire thing, 2 over x squared plus 1, is basically a constant. So I can basically take that outside of the integral, so 2 over x squared plus 1 times the integral from 0 to the square root of x of y dy. Now the integral of y is just y squared over 2. And don't forget we do have 2 over x squared plus 1. So I can multiply that by the constant. Notice that 2's will cancel. So we have 1 over x squared plus 1, which is just a constant, times y squared. Let's go ahead and evaluate it from 0 to square root of x. Remember, these are y bounds, so I plug it in for the y variable. So to evaluate, we'll get 1 over x squared plus 1 times, when I plug in square root of x for y, we get square root of x squared, which is just x, minus 0 squared, which is 0. So then I can rewrite it as x over x squared plus 1. So now that we have found the inside integral, let's go ahead and put it inside the outer integral from 0 to 1 times dx. Now realize this is just a simple u substitution problem. So if u equals x squared plus 1, du is going to be equal to the derivative of x squared plus 1, which is 2x dx. So then dx will equal du over 2x. If I go ahead and substitute that into the integral, we'll get the integral from 0 to 1 of x over x squared plus 1, which I made to be u, times dx, which is equal to du over 2x. Notice the x's will cancel. 1/2 can come outside the integral because it's a constant. So we get 1/2 times the integral from 0 to 1 of 1 over u du. Now the integral of 1 over u is just the natural log of the absolute value of u. We do have 1/2 outside as a constant, so we have 1/2 times the natural log of the absolute value of u. And don't forget u is equal to x squared plus 1, so I can go ahead and substitute that back in. 1/2 natural log of the absolute value of x squared plus 1. Now let's go ahead and evaluate that from the bounds of 0 to 1. So when I plug in 1 for x, we'll get 1/2 times natural log of 1 plus 1, which is 2, minus when I plug in 0, we'll get natural log of 0 plus 1, which is 1. Natural log of 1 is 0, so that'll cancel. And so we'll get 1/2 natural log of 2 as the final answer. So now for number 3, we have the double integral of e to the x over y dA described by region D. And so D is equal to inset notation for all xy ordered pairs, such that the y bounds range from 1 to 2, and the x values range from y to y cubed. So if I rewrite the double integral here of e to the x over y, realize that this time the x bounds have variables in them. So that is going to be up first in the inner integral, so from y to y cubed. Since x bounds are in the inside integral, we'll put dx on the inside. And the y bounds range from 1 to 2, so that will be on the outside with dy. So when I go ahead and solve this iterated integral, let's go ahead and write the inside integral first. So from y to y cubed of e to the x over y times dx. And so we are integrating with respect to x. So in this case, x is the variable and y is just a constant. So I can just do u substitution here. So if I make u equal to x over y, and so then du, remember we're going to derive with respect to x. So the derivative of x over y, when we derive with respect to x, is simply just 1 over y dx. So if I solve for dx, dx is going to equal y times du. So then if I go ahead and substitute it back into the integral, we get the integral from y to y cubed of e to the u, because I made x over y equal to u, times dx, which I made equal to y times du. Now remember, in this case we're integrating with respect to x, so y is just a constant. Now if that's a constant, I can take that outside of the integral, so we get y times the integral from y to y cubed of e to the u du. Now the integral of e to the u is just e to the u. We do have a y as a constant outside. So the integral is just going to be y times e to the u. I can go ahead and substitute x over y for u back in. And so now let's go ahead and evaluate from the x bounds of y to y cubed. Remember, we're going to plug this in for x. So I plug in y cubed for x, we'll get y times e to the y cubed over y. Now y cubed over y is just y squared, minus when I plug in y for x, we'll get e to the y over y, which is e to the first. So that's just e. So if I distribute over the y, we'll get y times e to the y squared minus y times e. So now that I have evaluated the inner integral, let's go ahead and evaluate the outer integral. So I'm going to put that, or I'm going to put y times e to the y squared minus y times e inside the integral from 1 to 2 times dy. Now we're going to integrate with respect to y. So y is going to be treated as a variable. So when I integrate y times e to the y squared, realize that this is just u substitution. So if u equals y squared, go ahead and make that the u. Then du, if we're going to derive with respect to y, is just 2y dy. So then dy is going to be equal to du over 2y. Now if I go ahead and replace that back in the integral, I'm going to rewrite it as y e to the y squared. So I'm just going to quickly rewrite the integral as it is. Now if I use u substitution, then I'll get the integral from 1 to 2 of y times e to the u, because I made u equal to y squared, times dy, which is du over 2y. So realize the y's will cancel. 1/2 can come outside the integral as a constant. So we get 1/2 times the integral from 1 to 2 of e to the u du. Now the integral of e to the u, let's go ahead and write that up here, is 1/2 e to the u. And I can go ahead and replace back y squared for u. And so that's what we get for the integral of y times e to the y squared. So now let's go ahead and find the integral of y times e. Now realize that e is a constant. E to the first is just going to be a constant value. Y is the only variable. So if we integrate y times e, we're basically going to have minus, as there's a minus here. Integral of y is just y squared over 2 times the constant e. And then let's go ahead and evaluate this integral from the y bounds of 1 to 2. So if I go ahead and plug in 2 for y first, we'll get 1/2 e to the 2 squared, which is 4, minus 2 squared, which is 4, over 2, which is 2. So 2 times e, minus, when I plug in 1 for y, we'll get 1/2 e to the 1 squared, so e to the first, which is just e, minus 1 squared, which is 1, over 2, so 1/2 e. So 1/2 e and 1/2 u will cancel. Those both minus each other will cancel. So we're left with 1/2 e to the 4th minus 2 times e. And that's the final answer. So now for number 4, we're trying to find the double integral of x times cosine y dA. And this time d is bounded by the graphs of y equals 0, y equals x squared, and x equals 1. So now we have to actually come up with our own x and y bounds. So if I go ahead and graph these 3 equations here, let's go ahead and actually move this over to the side a little bit. We have y equals 0, which is just the x-axis, y equals x squared, something like this, and then we have x equals 1. So let's go ahead and say this is 1. So we're basically looking at this region here. So this region is D. Now I'm actually going to draw another graph just zooming into that region, that specific region. So let's go ahead and draw like this. This is going to be region D. And so notice the x values range from 0 to 1. Since this is the graph of x equals 1, this entire line here, so the range of x values is from 0 to 1. Now the range of y values goes from the bottom equation of y equals 0 up to the top equation of y equals x squared. So if I were to write an inequality for x, well, x ranges from 0 to 1, and then for inequality for y, y ranges from the bottom equation of 0, y equals 0, to y equals x squared, that top equation, or the top function. So now using this information, I can rewrite it in iterated integral here. So we have the double integral of x times cosine y. Now y has the variables as the bounds, so that is going to be on the inside. So then we'll have dy on the inside. X has constants from 0 to 1, so dx will be on the outside. So let's go ahead and evaluate this. So if I rewrite the inside integral from 0 to x squared of x times cosine y dy, realize we're integrating with respect to y, so this time y is the variable, x is the constant. So the integral of x times cosine y is just x times sine of y. And we're going to evaluate from 0 to x squared. Realize these are y bounds. So if I plug in x squared for y, we get x times sine of x squared minus, when I plug in 0 for y, we'll get sine of 0, which is 0. So we're just left with x times sine of x squared. So now I can go ahead and put this under the outer integral from 0 to 1 times dx. So now we're going to integrate with respect to x. And so this is obviously just a u substitution problem. So if u equals x squared, du equals 2x dx. So then dx will equal du over 2x. If I go ahead and plug that in, we'll get the integral from 0 to 1 of x times sine of x squared, which I made it equal to u. So sine of u times dx, which is equal to du over 2x. Notice the x's will cancel. 1/2 can come outside the integral as a constant, so 1/2 times the integral of sine of u du. Integral of sine of u is negative cosine of u, so we get negative 1/2 cosine of u. Now I can go ahead and replace x squared back in for u. Let's go ahead and evaluate that from the x bounds of 0 to 1. So when I do that, plug in 1 for x, we'll get negative 1/2 times cosine of 1 squared, which is 1, minus when I plug in 0, I'll get cosine of 0 squared, cosine of 0. So we get negative 1/2 times cosine of 1, which I can't really simplify, minus cosine of 0, which is equal to 1. And so if I distribute that negative, we'll just get 1/2 times 1 minus cosine of 1. That's going to be the final answer. So now moving on to number 5, we have the double integral of y cubed dA, described by region D, and D is going to be the triangular region with the vertices 0, 2, 1, 1, and 3, 2. So let's go ahead and draw this out here. We have a triangle which has the vertices 0, 2. Let's go ahead and draw 1, 2 here, 1, 1, and then 3, 2. So this is going to be the region D. Now there's a couple different ways to approach this, but the way I see this is that the y values range from the y value of 1 to 2. So I can say that in an inequality, the y bounds go from 1 to 2. And I can go ahead and draw these two sides as two different line segments, because these will be two different functions. And I can see the x bounds go from the right or from the left function all the way to the right function. Now the equation of this left line, well, it goes up 1 over 1 to the left, so we can say negative x, or y equals negative x, and the y-intercept's at 2, so we can say y equals negative x plus 2. And so this equation, well, the slope goes up 1 and over 2, so it's definitely going to be 1/2 x, so y equals 1/2 x, and the y-intercept, I should have drawn this a little bit more properly here, but it intersects the y-axis at the value of 1/2. So I apologize for the drawing, but the y-intercept is 1/2. So now that we know the x bounds range from y equals negative x plus 2 all the way to y equals 1/2 x plus 1/2. But the problem here is that since these are x bounds, they need to be in terms, or they need to be in the form x equals, not y equals. So we go ahead and take each of these equations and solve for x. So let's go ahead and start with y equals negative x plus 2. If I go ahead and subtract over the 2, we will get y minus 2 equals negative x. And if I divide by the negative, we'll get x equals 2 minus y. So that left equation is going to be 2 minus y. X equals 2 minus y. Now let's go ahead and find what this right equation is. So if I go ahead and solve for x, I'll go ahead and subtract the 1/2. Or actually, before I do that, it's actually a little bit easier to factor out the 1/2. So y is going to be 1/2 times x plus 1. Now I can divide over the 1/2, or in other words, multiply by 2. So 2y equals x plus 1. So x equals 2y minus 1. So that's going to be the upper bound, 2y minus 1. So now if I were to write the iterated integral here, we get the double integral of y cubed. And so since x has the variables in its bounds, that's going to go first in the inside integral. I'm actually going to rewrite it so it's a little bit bigger. So we get the double integral of y cubed. And so the x bounds are from 2 minus y to 2y minus 1. And then the y bounds are just constants from 1 to 2. Since the x bounds are on the inside, we have dx, and then we have dy on the outside. So let's go ahead and first write the inner integral. So we get the integral from 2 minus y to 2y minus 1 of y cubed dx. We are integrating with respect to x. So if y cubed is a constant, the integral is just y cubed times x. Let's go ahead and evaluate from the x bounds of 2 minus y to 2y minus 1. So when I do that, plug it in for x, we get y cubed times, plug in 2y minus 1 for x, we get 2y minus 1, and then minus, when I plug in 2 minus y for x. So then if I simplify what's inside the parentheses, we'll get y cubed times 2y minus 1 minus 2 plus y. So then we get y cubed times 2y plus y is 3y. And then negative 1 minus 2 is negative 3. So then we get, when I distribute the y cubed, we get 3y to the 4th minus 3y cubed. I'll actually go ahead and factor out that 3. So we get 3 times y to the 4th minus y cubed. So now we can go ahead and put this inside the outer integral. So now we have the integral from 1 to 2 of 3 times y to the 4th minus y cubed. Since 3 is a constant, I can actually take that outside the integral, multiplied by dy. So now we're integrating with respect to y. So the integral of y to the 4th is y to the 5th over 5, minus the integral of y cubed, which is y to the 4th over 4. Don't forget we do have a 3 as a constant on the outside, so I go ahead and multiply by that. Let's go ahead and evaluate from the y bounds of 1 to 2. So when I do that, we'll get 3 times, now plug in 2 for y, we'll get 2 to the 5th, which is 32, over 5, minus 2 to the 4th, which is 16 over 4, minus, when I plug in 1 for y, we'll get 1 to the 5th over 5, so 1/5, minus 1 to the 4th over 4, 1/4. So if I go ahead and distribute that negative over to the parentheses on the right, we'll get 3 times 32 over 5 minus 16 over 4 minus 1 over 5, and then minus a negative, so plus 1 over 4. So then 32 over 5 minus 1 over 5 is going to be 31 over 5. So we get 3 times 31 over 5, and then negative 16 over 4 plus 1 over 4 is negative 15 over 4. And so I'm just going to go ahead and plug this into a calculator. And so when you use your calculator, you should get an answer of exactly 147 over 20. And that's the final answer.